though. I promise. I promise I'm getting better at not doing it. Come on, Matthew. What is that? I don't want that. I want this. We'll live with it, I guess. So, I don't know. Cole, what do you think the answer is to number one? It says, if the disk is going clockwise, the angular acceleration of the disk 10 seconds after starting from rest. So you actually converted it and said it's 28.26 and what radians per second squared? Okay, right on. Now, let's go to the net torque on the disk after 10 seconds. Koshi, what'd you get for it? Yeah. Oh, wait a minute. Just kidding. 300 RPMs. Sorry. Faster. Oh, great. What'd you get? 5.65 newtons per meter. See what that is. And then the angular velocity of the disk after starting from rest, we could use our alpha, and we could solve for this. So basically, 280, right? Cool. And then, oh, you guys couldn't see force. Oh, force says find the final angular velocity of the disk. Wait a minute. The angular velocity of the disk, 10 seconds after starting. And then the final happens after 40 seconds. Okay, so we'll take our alpha and we'll go to 40 seconds. Okay, so our alpha equals the final minus the initial. That's how we'll solve that. Okay? Right on. So to solve this, you've got 300 and you've got a revolution times 6.28, and that's how many radians you get per revolution. That'll cancel that out, and that'll give you radians. And then you got to realize that took place per minute. So if you want this to be per seconds, then you got to have 60 seconds in 1 minute. Times the 1 minute that it went for. So if you do that, you'll end up with your answer right there.
But the first one is angular velocity.
No, the first one's angular acceleration, number one.
But the given is.
Oh yeah, the given is RPMs, which is revolutions per minute. So, what I would do to solve that is just take your 300, and that's a revolution.
No, I've got radians. I would convert it to radians per second. But how do you go from angular velocity to acceleration?
Yeah. This is just going to get you the radians per second. So I don't know what that is, but that's radians per second. And then you got to put that back into the alpha equation. So, yeah. I'm sorry. I'm following you right now, sis. Okay. So you got a final. This ends up being the final velocity you reached, minus 0 over that 40 seconds. Whatever that number is, you put it in there, and that'll give you, I hope, 28.26. Did anybody else verify that? Does that make sense?
I got like 0.785.
Yeah, what?
0.785. So that's what I was asking.
What did you get 300 times 6.28 divided by 60. What's that?
I got 31.4.
So Cole, how did you come to here?
I didn't divide by 67.
There it is. You divided by 1 minute. Gotcha. So Cushy, right on. What's this now? So what's 31 divided by 40? Point what?
Oh, 0.785.
79. You like this? So then that changes this. Does your answer stay the same?
No, I just did it off of that.
So now we've got to change our alpha.
Yeah, it's 0.16.
And then that'll just change this slightly right here. You've got to put 0.79 in here. Set it equal to that. Probably not 280 anymore. There. Okay, man. We'll make this happen. So now we've got 0.79 radians per second squared equals, we're looking for so now that's 7.9. And then we'll find the final angular velocity of the disk. We don't even need this. We don't even need this. We can use this again. 0.79 equals x minus 0 over 40 seconds. So that would be 4 times bigger than this number. So it would be really close to 8 times 4. So really close to 32. Good. We tidied it all up. How about I okay. Pass some things back. Ladies and gentlemen, this test was out of 35. This test was a pretty difficult test, so I want you guys to take this with a little grain of salt. And I'll explain to you I'll explain to you how well I think we did on this test. Even though this test was somewhat difficult. Okay? Let me give you guys. So my RLA children, if you do not mind, go ahead and open up your exam. Oh, Ashma's not here. So, Ashma, I've got your test. I'm going to put it on the desk. You guys give me 1 second, and we will go over this. We turn the light off. There will be test corrections. Promise, ladies and gentlemen. And, oh, does anybody else have their tea time for me? Does anybody else have this tea time lab done for me? I am just curious. Did you turn this in digitally? What's that? Yeah, it's due at midnight tonight. That's what we're doing at night. We want to actually in paper. Oh, you guys aren't done with it? Well, I can give you time to work on it in class. I have no problems. I assume you guys are done. Hey, no worries. No worries. It's due at midnight. I figured you guys want to turn it in a paper. You want to upload it, man? I don't got a problem with that. No problem. Ugh. Sorry, I'll turn my phone off. think you guys did a really nice job in general with how conceptually different this unit tends to be. All right? This test was out of 35 points, but it also, because it's a test, it gets factored in at 1.5. So you should be saying to yourself, Mr. Matthew, that seems completely awful. It seems like I did terrible. But here's the deal. We have not done an exceptional amount of paper exams. We haven't done an exceptional amount of what I call authentic checking of our knowledge. When you give a take-home exam, you're testing usually a kid's ability to research a problem and look up an appropriate answer. All right? And I'm not saying there's no value in that. When you do a Schoology test and people are doing multiple choice, you're testing people's ability to put in answers in a multiple choice Schoology format. So if you want to do authentic testing, oftentimes you just have to sit people down and you have to go over the test. So let's talk about what kind of answers AP is really looking for. AP Physics C, if you can get an 80% or above on the test, you're going to get a 5. All right? If you can get a 70%, you're going to end up with a 4. If you can get a 60% or above, we're going to consider that a passing grade. So with your calculator, I want you to assess what percentage you got right out of 35. And I can tell you right now that the class average on this was minus 12. So that's about 23 divided by 35. The class average on this, believe it or not, right in between a 4 and a 3. So you might be sitting there telling yourself, man, I got clobbered on this thing. No, I gave you a test that is absolutely AP Physics C red. So right now, if you were to take the test, and this is how you perform, you're getting a 3 at minimum. Let's go over these answers. There's going to be test corrections. Please feel free to write whatever notes you want on your sheet as we're going over. All right? So for number 1, I'd say over half of you got this right. If the angular velocity is 0 at all times, you're not accelerating. If it's 10 at all times, you're not accelerating. If the angular displacement has the same value at all times, you're not moving in a circle. If you're having trouble converting angular in your head to something that makes sense, why not rewrite all these questions in your mind like this? The linear velocity is 0 meters per second at all times. Oh, I'm not accelerating. The linear velocity is 10 meters per second at all times. Oh, I'm still not accelerating. The displacement, D, has the same values at all times. Well, then I'm thinking of a graph where my position to time looks like this. I'm still not accelerating. It just seems difficult because that omega makes it look trickier than it is. It shouldn't be that way. For instance, if I want to know the angular displacement of a particle that completes 6 revolutions, well, then I just need to set up my 6 revolutions times 2 pi, and I'm all good. It'll be 12 pi. That was pretty easy, though. I think most of you rocked that one out pretty well. When it comes to question 3, I looked at it like this. It wants to know which ones are true. The kinetic energy is different for each point on a circle. That's true because all dots have different radiuses. The angular acceleration is the same at every point. Angular acceleration is the same. The linear velocity is not. So I just found my false one. And that gave my answer as D right there. Number 4 is pretty easy. All spinning objects conform to mr squared as a base and then go to a 12, a third, a fifth, whatever, 2/3, 2/5. If you double an object's mass, what will produce a greater increase in inertia? Do I double this or do I double this? And you knew the answer was that. I think you all might have gotten that right. Lots of people miss number 5 because number 5 seems difficult. For number 5, here's what I did. I said torque equals IA and torque can be FR. The I of a solid disk is half mr squared, so I sub that in, and then I cross multiply, and then I isolate. Okay? If I want to make this number minimum, if I want to make this number go down, I want to make those numbers go up. I want M and R to be as large as possible. Okay? That's the biggest change you can do. Okay? So yeah.
Why is making the edge as big as possible better than making it as small as possible?
You would want F to be as small as possible. Oh no. So I want M and R to be as possible and F as small as possible. Wait a minute, the answer to this is C. It's the wrong answer key for this problem. Who did I mark off for that? Oh, I'll have to go back and check that. I gotta go back and give you guys points for that. My apologies. Duh. Geez, that answer's C, man. Good job. That answer's C. Thank you. That's C. That'll be the only one, I promise. But yeah, that's totally C. That doesn't even make sense. That F is as large as possible. Whoa, whoa. Snapshot? Sure. There you go. What even is this? Ladies and gentlemen, question 6. You're literally just differentiating twice to get to E. When I look at 7 and 8, they're both kind of similar, but angular momentum stays the same, but the kinetic energy will not stay the same. If you increase W, then you're going to get more kinetic energy. So that's why that has to increase. Number 8 is IW equals IW. That should make sense. These 9, 10, and 11, I'm just going to let you guys stare at 9, 10, and 11 for a couple seconds because 9, 10, and 11, that really did stretch what we know. That really did stretch what we know. So let me have you look at those for a second. Oh, I can't believe I didn't notice that. It makes me so mad. So mad. Hey, everybody, when it comes to 9, it's a meow me problem. And then I just had to take out the angular portion of that. So obviously we say mgh equals half mv squared plus half mv squared. To make that combine mathematically, we would take 1/2 of mgh. For number 10, that's literally right out of our unit notes that we have double the values of A compared to B. 11 is very tricky because 11 did not leave the problem in mu mg plus mg sine theta. You know what you got to do with 11? You have got to do a mental trick. You've got to say that mu mg cosine theta, which is the force of friction, creates a negative ma. So, in a real mathematical world, mu mg cosine theta plus mg sine theta equals ma. That'd be great if they would have left it up in here. So we had to make a substitution where we know the force of friction reduces according to negative ma. So if you put negative ma into this equation, you will end up with mg sine theta equals 2ma. And that's the same thing as dividing by 2 on both sides. So a equals 1/2 g sine theta. That's complicated. I get that. That's a little tricky. I also get that. And then 12 was just a regular, really vocabulary, almost. For 13, I set it up like this, knowing that v is the same in all parts. I said RW equal to RW. The W's are not the same. And then for 14, I came through with this. And that got me, that 14 ironically is 14 ml squared. It just worked out that way. That's not intentional by any means. I'm not that clever. And then for 15, oh, sorry, for 15 I solved. There. I used power in the kinetic energy equation for 15. And are there any questions on 1 through 15 right now? We okay? They cool? Okay. Look, we need to have a discussion about this AP Physics C problem. We all missed a lot of points on this, and I am partly to blame. We have not done enough free response style questions in here due to lack of time. We're going to do a lot more in the next month. But, you know, the time constraints have really eliminated our ability to do these. We've got to do more. And what you're seeing is a little bit of the result of our inexperience for solving AP Physics C problems. Sorry about that, too. There. So, people, I'm an AP Physics C, and I'm an AP Physics 1 grader. And here's the way you have to solve these problems to get maximum points. It says calculate the linear acceleration A of the falling block in terms of the given quantities. Okay? It says a solid disk of an unknown mass and known radius r is used as a pulley in a lab experiment, as shown above. A small block of mass m is attached to a string, the other end of which is attached to the pulley and wrapped around it several times. The block of mass m is released from rest and takes a time t to fall the distance d to the floor. Now, it is true on the one hand that if I looked at this in terms of mg, and I looked at this in terms of maybe tension going up, and then I knew that acceleration is going down, a few of you said that the F net in this scenario is going to be T up minus mg equals ma. I allow this to be credit. But on the AP exam, this isn't credit because you did not plug this in to this equation or acknowledge it in any way, shape, or form. But if you want to know the true linear acceleration, you can ignore this and use a kinematic equation because this distance that this block covers will have that factored in. You got 1 point for this, and you got 1 point for setting an A equal to 2d over t squared. That's how you earn 2 points. A lot of you went into this type of a scenario. Or, like I've said over there, that T minus mg equals minus ma scenario. Okay? Do you want to know why this isn't right and this isn't right? It's because of this sentence right here. The reason why this can't be correct is because of this. Did they give you an I yet in the problem? No. Well, then you can't use it. Did they give you tension yet in the problem? No. So you can't use it. You know what qualities they did? The quantities they did give you? D. They gave you an R. They gave you an M. The M doesn't dictate the acceleration directly, so you just need to use the 2D in that. Oh, they gave you a T as well. I see a T right there. So you have to use their terms. So we just need practice on recognizing what they're asking us, and then I think we'll become much better problem solvers. Look, they gave some latitude here. The best answer for this is D versus T squared or V versus T. Lots of you went out of your way to describe these, so you get a point. But look, I had a couple of you that did this, and you didn't explain your reasoning. This is not an explanation of your reasoning. This is an equation that you provided. Good job. You earn a point for that. But you must explain using words that I will take the slope of a D versus T squared, because that is mathematically acceleration. I will take the area of a V versus T. I will take the slope of a V versus T graph because that is acceleration. Okay? You've got to be descriptive with your words. And then let's take a look at this right here. Data that is consistent with the graph. You've got to get a D versus T squared graph. If you plot a D versus T graph, you're going to get velocity. And that's not acceleration. Or you could have put a V versus T graph here, and that slope would be acceleration too. But here's the deal. They didn't want you to do a V versus T graph. You want to know why? Because you didn't need to do that. You could have just taken these right here, and you could have plotted what you needed to apply to get acceleration. And here's where a big step needs to occur. If you want to use your graph to calculate the magnitude of the acceleration, do you notice that I have to double my displacement from here to get my real acceleration? Yo, Matthew, why do you have to do that? This is the real equation right here. When I go to make my graph to get acceleration and isolate it, that would be 2 times y over t squared. So you can get the slope to get the acceleration, but you've got to double that value. Okay? So it seems like a small thing, but it's technically accurate. So there you go. They gave you a point for using the equation correctly, and then there is another point for using their values correctly. I think we probably had the most difficult time on the last question. It says calculate the rotational inertia of the pulley in terms of M, R, A, and a fundamental constant, which is gravity. That's why we can't leave it in terms of T. So they gave you 1 point for acknowledging that T times R equals IA. They gave you 1 point for a connector equation. Now, I thought most of you gave this a really nice try. And most of your reasoning was sound. I am going to emphasize the fact that you could get this and this. That's so simple to get those two. This little substitution equation is not where you're allowed to end. I had somebody give me this as an answer. In my heart, I want to give you full credit for that because that is a right answer. But you know what? MRA and a fundamental constant. You know that T is not a fundamental constant and it's not M, R, or A. So you can't leave it here. Math, that's jacked up. What do I have to do? You have to do substitution to make the T go away. Now you've got fundamental constants. So you get 1 point for acknowledging you know that T has a place in this problem, and then you get 1 point for the final answer. But I did have a few of you get this final answer. Hey, ladies and gentlemen, this is tough. This is tough stuff. This is a dog-eat-dog world. I get it. That's how you get 15 points on this problem. That's how you get 15 points on this problem. So here's what I'm going to do for you guys right now. Watch you guys do your test corrections. Now that I just went over this, and I'm here and I can answer your questions, why don't you guys pull out a blank piece of paper and let's do the test corrections. RLAs, you guys can do your test corrections and submit them to me. They are not due by the end of today. They're not due by the end of today. I'm going to make them due probably by the Wednesday we get back. But I'm done with you guys. Okay, RLAs, you guys, I hope you have a wonderful spring break. I'm proud of both of you. You did well on the quiz. So good job, in my opinion. But you guys can go. Did you have any questions on your test that you wanted to ask me or anything? Okay. Well, then you boys have a good spring break, okay?
You too, Mr. Mackey.
Thank you. Thank you. I sure will. Don't you worry. I'm out of here. You guys can sign off with me. Oh. And then let me get rid of my